Hi friends, let's begin with the first course of our discussion, which is linear algebra, and the topic for today's discussion is linear dependence and independence. So first of all, we are going to define what do we mean by linear dependence and independence, and then we are going to look at some of the previous year questions to get an understanding of what type of questions are being asked in this exam. So let's begin with the definition itself. So let's say we have been given a set of vectors v1, v2 up to vn, and then we say that this set of vectors is linearly independent if summation ai vi equals to 0, where I varies from 1 to n. It implies that ai equals 0 for all values of I belongs to 1, 2 and n. So basically when we take a linear combination of these vectors and it is 0, so we say if this implies that all the coefficients are 0, then we say that this set of vectors is linearly independent. And then what does this imply? So this implies that there is no vector in the set V which can be expressed as a linear combination of other vectors in the set, and the set of vectors is otherwise called linearly dependent. So to check if a given set of vectors is linearly independent, what do we do? So the working rule is to reduce the row matrix of the given vectors into its echelon form. And if there are no zero row vectors in the echelon form, the set of vectors is said to be linearly independent. And if there are any zero row vectors in the set, then it is called linearly dependent. So one more point to note is the determinant of the row matrix of the vectors is 0 if the vectors are linearly dependent, and it is non-zero if the vectors are linearly independent. Okay, so having looked at the basic definition, what does this imply, and what is the working rule to check if the given set of vectors is linearly independent, we now move on to some of the previous year questions. Okay, so in the first question we have been given some vectors and we have to verify if these are linearly independent, and we have to justify our answer as well. In the second questions we have to show that the set of vectors x1, x2, x3 are linearly independent over the field of real numbers, but these are linearly dependent over the field of complex numbers. In the third questions, we have to show that these three vectors are linearly independent in R3, but the linear transformation which is defined by this relation, so the images of these vectors under this transformation, these are linearly dependent. We have to prove this and give the reason for the same as well. Now we have to determine in the fourth question whether or not the set e1 minus e2, e2 minus e3, like this en minus 1 minus en and en minus e1 is linearly independent. Okay, so what are e1, e2, en? These are the unit vectors in n-dimensional spaces. So in the fifth question we have to find the values of k for which the given vectors are linearly independent. And in the last question, sixth question, we have to show that the vectors, these given three vectors, form a basis for the vector space. So when do the given vectors form a basis? Two conditions. First, they span this vector space, and then second condition is they are linearly independent. Okay, so now let's look at each of these questions individually. So in the first question, the vectors v1, v2, and v3 and v4 are linearly independent. Is it true? Justify your answers. So what I'll do is I'll just go through the solutions. Okay, so what you are supposed to do is just pause the video, look at the question, and then try to solve it yourself, and then look at the solution only if you're not able to solve it. Okay, so I'll begin with the solution. So first what we do is we form the row matrix of the given vectors, which is this matrix: first vector, second vector, third vector, and fourth vector. Then I apply row operations on second, third, and fourth row, which are r2 minus 2r1, r3 minus r1, r4 minus 2r1. The objective of applying this row operations is to create leading coefficients as 0 in the second, third, and fourth row. Okay, then I try to create 0 here and here, so I apply row operations to r3 and r4. So these are the row operations that I apply. I get a 0 here as well. Here I get zeros, here I already had zeros, and by doing that I get zeros here and here as well. So as we can see, there are two zero row vectors in the echelon form, and since the echelon form of the matrix contains zero vectors, this implies that the given set of vectors are linearly dependent. So now let's move on to the next question, second question. So we have to show that the vectors x1, x2, x3 are linearly independent over the field of real numbers, but are dependent over the field of complex numbers. Okay, so first, if we take the summation ai xi equals to 0, okay, I belongs to 1, 2, 3 because there are three vectors here. So what do we get? So we get a1 times first vector plus a2 times second vector plus a3 times third vectors equals to 0. We solve these equations by taking we equate these x, y and z coefficients of the summation to 0. Okay, we equate individual x, y and z coordinates to 0. So first we get, when we equate the x coordinate to 0, we get a1 plus iota a2 plus this is 0. So a1 plus iota a2 is equals 0. Then we get 1 plus iota a1, 1 plus iota a1 minus iota a2 minus iota a2 plus 1 minus 2 iota a3 plus 1 minus 2 iota a3 equals to 0. This is the second equation. Then in the third equation we get a1 times iota plus 1 minus iota, which is this, times a2, which is this term, and then 2 minus iota times a3 equals to 0. This is the third relation. Now we consider two cases. First is when these coefficients belong to the field of real numbers, and then second case when these a1, a2, a3 belongs to complex numbers. So first is when these belongs to R, and second is when these belongs to C. Now we solve these equations, and from the first case when a1, a2, a3 belongs to R, we get a1 equals to a2 equals to 0 from the first relation, and when we substitute these values in either 2 or 3, we get a3 equals to 0 as well. Okay, and here if we do the same, we get a1 equals minus iota a2 from the first relation, and from the second and third relation we get a3 equals minus a2. Okay, so in the first case where a1, a2, a3 belongs to R, summation ai xi equals to 0. This implies that a1 equals a2 equals a3 equals to 0 because all three of them are 0. So if summation ai xi equals to 0, this implies that all three coefficients are 0. Then this means that these three vectors are linearly independent over R. But here we don't get this such relation. Instead we get a relationship between these three coefficients. So we say for this case that summation ai xi equals to 0 does not imply that all three coefficients are 0. Therefore x1, x2 and xc are linearly dependent over C. Or in other words, we can write any of these vectors as a linear combination of other two vectors. Okay, next move on to the third question. We have to show that the vectors 1, 1, 1, 2, 1, 2 and 1, 2, 3 are linearly independent in R3. That's a very simple case. We simply reduce the row matrix to the echelon form. Okay, and then let R3 to R3 be a linear transformation defined by Txyz equals x plus 2y plus 3z, x plus 2y plus 5z, 2x plus 4y plus 6z. And then we have to show that the images of above vectors under T are linearly dependent and give the reason for the same. So for the first case, we form the row matrix. Okay, 1, 1, 1, 2, 1, 2, 1, 2, 3 reduces to its echelon form by applying row operations here first, and then to R2 and R3. And to obtain this matrix, then we apply row operations to third row to obtain this matrix, which is the echelon form, no zero row vectors. Therefore these vectors are linearly independent in R3. Now we take the image of the vectors under this transformation, and so we take the image of this vector 1, 1, 1, 1, 1. So this is, we get the image as 6, 8, 2. Then we take the image of 2, 1, 2. We get 10, 14, 20. Then we get the image of 1, 2, 3. We get the image as 14, 20, 28. Now we reduce the row matrix of these vectors into its echelon form. We get this form, and we can see that we have a zero row vector. Therefore we can say, since the echelon form of the row matrix of these images of these vectors contains a zero vector, therefore the images of the given vectors under T are linearly dependent. Cool. Now this is a very easy and straightforward question. We have to determine whether or not the set E1 minus E2, E2 minus E3, En minus E1 is linearly independent. Okay, so we form the summation ai vi equals to 0. What does this imply? A1 times E1 minus A2 plus A2 times E2 minus E3, like this. An times En minus E1 equals to 0. Now what we do is we take the coefficients of E1, all the coefficients of E1. So A1 here and minus An from here. So A1 minus An E1. Now we take the coefficient of E2, A2 from here, and then we get from the next term, where are we getting okay, from this term we get A1. So for E2 we get A2 minus A1. Similarly we form all the other coefficients and their products. So we get An minus 1, En equals to 0. Now this is like summation of ai ei equals to 0, and since ei's are linearly independent, it means all the leading coefficients should be 0. This means all these leading coefficients a1 minus an, a2 minus a1, these all should be equal to 0. So now this implies that all of these numbers should be equal to a constant, let's say k, because a1 equals to an from this equation, then a2 equals a1, which is also equal to an, and we can similarly follow this recursive equation, recursive solution to see that all of the coefficients are equal to a same number, let's say k. So this means that they are not equal to 0. They could be anything, any constant, but they are not. That doesn't mean it is essentially equals to 0. It might be 0, might not be 0. So this means that the set is linearly dependent, because it doesn't, because their summation ai vi equals to 0 does not imply that ai equals to 0. Okay, so therefore the set is linearly dependent. Now we have to find the values of k for which the vectors, these given vectors, are linearly independent. Okay, so the given vectors are linearly independent if the determinant of the row matrix is 0, 1 1 1 1 3 minus 2k, and this third vector as the third row and fourth vector as the fourth row, we apply column operations to c2, c3 and c4 to obtain 0 here. Then we reduce the determinant to this matrix. Okay, and then we apply row operations to r3 to obtain 0 here, and here we apply r3 is r3 minus 2r1, and then this is the determinant. This is k minus 5 whole square into k minus 1. This should not be equal to 0 if these vectors are linearly independent. This means k should not be equal to 1 or 5. Now next and the last question: show that the vectors, these three vectors, form a basis for the vector space R3. Now the given vectors form a basis if the given vectors, if satisfy two conditions. First, they are linearly independent, and second, they span R3. So for the first condition, since the determinant is non-zero, the determinant of the row matrix of these vectors is non-zero, therefore they are linearly independent. Now let xyz be a point in R3. So a1 times first vector plus a2 times second vector plus a3 times third vector, that is the linear combination of these three vectors, can be written like this, and this should be equal to a point in R3 which is xyz. So we can find relationship, we can find a1, a2 and a3 as a function of x, y and z. So therefore for any point xyz in R3 we can represent it as a linear combination of three vectors a1, a2, these three vectors. Okay, so therefore since these vectors span any, since xyz is a generalized point, so this means it can be any point. So it means the linear combination of these three vectors span R3. So therefore from 1 and 2 we can say that the given vectors form a basis for the vector space R3. So thank you and have a nice day.